China came up with this new revelation, big fusion power breakthrough. But it's so interesting. It's really the same kind of thing that I keep pointing at, which is that the fusion power seems to be always, no matter what point in the last 20 years we're at, the fusion power is 10 years away. If you actually read this article and start to unpack what's going on, they built this huge tokamak reactor. These tokamaks are the gaseous plasma that are confined by these huge magnets, and they're trying to squish these atoms together. It's all well and good. They're very proud of themselves, but if you go down, you eventually get to a point. Let me see if I can find it. It's really hard to read this upside down. You know, the reactor as a whole still used more energy than it consumed, right? So these breakthroughs almost always, if you read the fine print, this one's actually in the article, which is why I wanted to show you guys. Generally speaking, these are really, really powerful machines that require gobs of energy, like the equivalent of a power plant to make them run. So this technology is still a little bit out of reach. And I think I just wanted to show you guys that as an example of what we're up against here. Other than that, I want to hear from you guys. Today, just to preview it, or this week, I suppose it's a new week, we are going to be setting up the last few pieces that we need. So again, the goal of this whole class ultimately is to build out some approach to a cosmological picture of the whole physical universe. To do that, we need to understand how stars work, or at least, different theories about how stars work. The next piece of that puzzle is how stars are built. So we have to talk about the building blocks for stars, and that involves looking at all of the stuff in between the stars. So the interstellar medium. So that's what we're going to work towards in the back half of this week. And then along the way towards understanding cosmological picture, we need to understand and wrap up this idea of how we tell how far away things are. And so today, we'll mainly, I think, focus on how far away things are, and then we'll start to get into the interstellar medium. And it turns out that the way that we build out these distances is much easier for things that are nearby than things that are really far away. And we have to combine a bunch of different assumptions the further we get away in distance from our own solar system. And I want to look at that because what we're going to construct is this thing that astronomers call the distance ladder, which is essentially this series of assumptions you make where you know how far something close by you is, use that to judge how far you think something a little bit further away is, and then you keep building on the previous layer of abstraction until you get out to really, really far distances, which are then used to construct a cosmological picture of the whole universe. So it's really important stuff, but I think it's a good day to set up the distance ladder, or the idea of the distance ladder for you guys. Now, before we do that though, let's chat a little bit. Let's get a little conversation going here about what we talked about last week, which was largely building this picture out, the good old HR diagram. So the temperature and luminosity relationship, the power output of stars versus their temperature. And we're going to come back to this. We're going to do the different models for what this all means. And I kind of previewed it last week, but I'm curious to hear your guys' thoughts about it.
Yeah, the more fusion a star has, the more output of light the star will have.
Nice. Yeah, that's the fundamental assumption of the picture, which is fairly reasonable. The bigger something is, the more pressure you have available to do this fusion business, in any case, no matter how it's done. And so that does seem to be the big story behind why most of the stars, most of the bright stars seem to be the hottest stars too, right? So we have these spectra of temperature, but temperature is actually kind of running in reverse here. So over here, hot stuff, most of the hot stuff tends to be really bright. So you have this nice line. What else? Anybody else have something to add to that idea? Thoughts? Yes. Remind me your name again.
Arthur.
That's right, yeah.
I remember that we were talking about
That model that we had written was outdated and that we had to add stuff to kind squish in the new ideas instead of changing it.
Yeah, that's a theme that keeps. Sorry, I'm looking for your name on here. Gotcha. Yeah, that's a theme that keeps cropping up over and over again too, which I think is like perfectly natural. Trying to adjust to adopt these new systems. Obviously, the lettering of the spectral classes makes no sense. That's just kind of a, I don't know, a shallow version of this idea that we kind of tend to build on old ideas that don't make sense. Now, that might have very little impact, right? Because we still understand the spectral classes related to temperature. But it might also have really big impact in terms of understand how these things work. Yeah. Is it Aiden?
Yeah.
Yeah.
Is there anything that isn't put inside of this that, like you said, more mass, it has more to do the fusion and everything? Is there something that isn't following that grid, like smaller, but still able to produce more?
Well, if you look at the diagram, that's kind of the story that we there's some weird pieces of this puzzle, right? These guys are really weird down here. These white dwarfs, right? I think they're going to play a central story. They're also related to this weird black hole business that we'll get to eventually. They're really, really hot, but they're really dim. And so they don't fit neatly onto the story of the main sequence that goes with this bigger, brighter fusion business. We will circle back on white dwarfs, but I think I introduced the concept last time. Actually, I'll let somebody else do it. What did we talk about for white dwarfs last time? Anybody? Yeah. Remind me your name again. Sorry. Cassandra, that's right.
We talked a bit about like the two main theories behind. I don't remember what the second one was, but I remember the first one was that they're squished down a whole bunch, and that's why they're powered, and that's the main one they're going with.
Yep.
And then to add on to that, like the second theory was that they're red giants that have like burned through all their fuel. So they're like basically dying because they can't keep that equilibrium anymore.
I think that's probably true no matter which theory. There is another theory though that I threw at you guys last time. Anybody? Lattices, my friends. Lattices. Anybody remember this idea? That's okay. Yeah.
It's saying that going back to how they fuel and saying that maybe the fuels happening, gases happening, liquid and oxygen, and the boxes switching down and the atom together. It's just like being raised.
Yeah, so the important part there is that, okay, if there is actually a lattice structure, two stars, in fact, in other words, if they're not just some inchoate, like unformed gas, and they actually have structure just like liquids do. And most people don't think, this is hard for people because they don't think about, water in the ocean as having layers to it. It actually does though, they're very transient. So water forms these very, like the individual water molecules will swap out of the actual, I don't want to say crystal, but that's probably the easiest way for you to understand it. There's actually kind of a mesh network of water molecules. And the individuals, especially when you get down lower at the bottom of the ocean, there's a lot of pressure. There's substrate at the bottom of the ocean to organize the water molecules. You actually get these individual layers of water. And there's ways that we can figure that out with different types of instruments where we can actually push on the water and punch down through individual layers at the nanoscale. So the idea is that, yes, the lattices actually change the optical properties of things. I've mentioned this before. I'm going to keep saying it until you guys answer this question when I ask it at the beginning of class. Diamonds and graphene are both made out of pure carbon, but they have wildly different optical properties. The same thing was true of any material that has a true lattice structure to it, so liquids and solids. They have wildly different properties. And so when people were coming up with the model of white dwarfs in the early days, this was back in the 20s when people noticed that there was some outliers on this diagram very quickly. And when they were thinking of what in the world would cause something to be so hot to be so dim? The only thing that they could think of in the gaseous model was that it was really small in radius. So that's the standard model of white dwarfs, is that their radius is really small. The other piece of the equation that gets ignored, though, is this concept of emissivity. Somebody emailed me about emissivity. Who was that? Yeah, Hannah, right?
Yeah.
So Hannah emailed me to go over this a little bit more. There's another factor in that equation that isn't just radius related, and it's emissivity. The emissivity depends on the lattice structure of a liquid or a solid, right? So it doesn't matter much to a gaseous model. But if the stars have some true structure, if they're actually more liquid-like, at least at their surfaces, then you run into this situation where you actually have to consider the structure of that entity, how those atoms are arranged with respect to each other, because that emissivity can actually change how much light will be absorbed or emitted from the surface of that body. And so obviously diamonds are a great example of this. They have way less than one emissivity. They're almost translucent. And so they don't absorb light, which means they don't emit light either. If you heat them up, it's very, very hard to get a real proper temperature off of them. So those are really the two competing theories of white dwarfs. We'll circle back on it. I really want to make sure that you guys understand this component before you're let loose on the world after this class. Thoughts, questions? Yes.
So I was wondering, because the main sequence of the graph, it kind of is like a little curve.
It is a little curved.
Why isn't it like linear? Because shouldn't it, like, for the main sequence, shouldn't it be like more like?
It's a really good question. I wonder if it was linearized. So I'm just looking at this now for the first time after you asked that. It seems to be a log scale of some sort. So if you see this is 3,000, twice 3,000 is 6,000. And then, the next bar is 10,000, right? Which is almost in the order of 2 times that. So it seems like it's not a linear scale. Maybe if it was linearized, it would appear to be more of a linear relationship. I think that, though, it actually has more to do... I actually don't think it would be linearized. I think it would still have a curve to it. And that's because the power of the luminosity depends on... the output of the power of the star, the luminosity, depends on the 4th power of temperature. So it's actually an exponential relationship, which honestly would probably result in an even greater curve if we were to plot it against temperature. But they logarithm it, make it a log scale, so it's flattened out a bit. What else, guys?
So if these other stars are made out of liquids, and that their black body spectrums and the colors they put off aren't based on temperature, but on their material composition, and that comes down to lattice structure, right? Or atom structure. How can we know that just by the light readings, what they're actually made out of? Or is that one of those things where we think it's made out of something, but without actually getting a sample of its core, we would never really know exactly what's going on there?
It gets very tricky. So even if we start with our own sun, where, one of the biggest mysteries, like even if you talk to a NASA scientist, they're still trying to figure out how in the heck it is that the solar atmosphere is at millions of Kelvin, let's say, but the surface, the black body temperature is only around 6,000. It's very strange. It's kind of like if you had an oven whose oven walls were room temperature, but the air inside the oven was at thousands and thousands of degrees. Like, it would be very hard to imagine how that was even possible. So it's perplexing, and some of the answer is technical in that we're talking about a really weird definition of temperature, which is the average kinetic energy of the particles. So it's like, that's part of the story, but I think part of the story is that the surface of the sun is probably a lot hotter than 6,000 degrees. But a lot of that energy isn't going into the lattice to generate the light. It's actually going into all those convection cells, the motion of the surface. Remember, the surface of the sun turns faster at the equator than at the poles. So there's goop moving around and dissipating friction. There's heat moving all throughout it. It's not really at equilibrium with its surroundings anyways. There's a lot of heat coming off of the sun. And to get a true black body temperature, you have to be in thermal equilibrium with the enclosure that you're measuring. That's obviously not the case with the sun. So I think there's probably a way to deconvolve the true temperature of the sun once you accept the premise that it's not a gas in the first place. But it gets complicated and you have to start factoring in things like convection, how much is the surface rotating, and I think that will be available for other stars, but it complicates the picture for sure. So, I think that being said, when you see something that's glowing blue hot, it probably is hotter than something that's glowing dim red, right? How much hotter though, like in terms of like what is the actual numeric assignment to it? I don't know that we can do that immediately, but we can probably compare them to each other as long as it turns out that stars are more or less similar in the way that they are structured at the surface, right? They do seem to be mostly made out of hydrogen. And so presumably all the stars, even the assumption in mainstream astronomy right now that the stars are all basically the same thing, there's just more stuff on some of them than others. There's more hydrogen in one place on the big blue ones. So there's probably a way to back calculate, even if we factor out convection and stuff like that. This is a good question though. What else do we got, guys? Yeah, Jasmine.
So, last week on Thursday, you spoke of black holes that were later classified as stars.
Mm-hmm, mm-hmm.
So, how would we be able to classify those? And also, would they be classified onto that diagram, or would they get a new type of star?
Yeah, so most of there's more and more of these black holes that are turning into stars every year. And it generally comes down to they're getting moved into this white dwarf category because they're really dim, right? And we didn't see them when we first looked out. So Sirius is a good example. When we first started studying Sirius, we didn't realize it had a partner to it because it's a really, really dim partner. It was only after we started looking at the orbits and the wobbles that we thought, oh, wait, there's something else going on here. Now people think Sirius might have a third partner because of the way that the orbits are wobbling and so forth, although it's difficult to resolve that. And so a lot of these stars that are turning from black holes in the categories into white dwarfs. So black holes, just to preview it, they're kind of an extreme version of white dwarfs. There's something that is part of an orbital system, generally speaking, that we can't see. So a star seems to be orbiting something that we can't see. It's too dim to even emit light to fit even on this diagram. It would be down below, down off the chart down this way. But it has a lot of mass to it, so technically it should have a lot of luminosity. So they're really weird, and we'll deal with that phenomenon later. But again, there's an ultra-mundane explanation for such things, right? Which I'll probably come back to, which again has a lot to do with lattice structure. And there's a really exotic explanation which has to do with new forms of undiscovered matter and stuff like that, rips in physics and whatnot. We'll have plenty of time for all of this though, but it is very much an extension of the white dwarf story. So that's a really good point. But don't worry, we'll have more time for both white dwarfs and black holes as we move forward. What else? Is Shay still in this class? Yeah. All right, you guys let me know if you know any of these people who have dropped it. How about Jeanne? Jeannie. Okay. Tell her to send me an email. Let's see here. Is Tirza here? Nope. How about Elizabeth? Nope. How about Amy? Are you still in this class? I don't think Amy's in this class anymore. How about Alex, Emily? Nope. All right. Let's see. Is Ray still in this class? Yes. Hello. Any thoughts from last week? Okay. Well, check out the lectures and email me. Let's see. All right. I think I've made it through everybody on this list. Nope. Is Genesis still in the class? How about Caleb? He is still here, but not here. All right, and Carlos? Excellent.
I have that there's Maybe there's like two different ways to get the same answer for which one would lessen.
Yeah, that's what we were talking about with the radius versus the emissivity. I know that word emissivity is really like something you're not going to encounter in your daily lives, but you got to remember that any sort of object that can absorb a certain light, it can also give out the same light when it's heated up. So, this black tabletop is black because it's absorbing all of the different frequencies of light, but it can also give off all of the same frequencies too when it's heated properly. Of course, this would combust at some temperature if necessary. But like a soot-covered chamber, for instance, would give off all those frequencies of light because it's black. So that was the piece of the equation that kind of gets ignored in favor of radius due to the gaseous nature of the state equations for the stars at this moment right now. I think that's going to change though. But that's a good point. What else? Let me see. I actually do have a couple more people. Emily Bunton? Nope. How about Asante? And Stella? All right. You have a very tiny voice. I'm struggling to hear you. I'm sorry. Yeah, some of them along those same lines. So you're saying it's interesting how big the stars are compared to like planets and things like that. It's sort of true, but it's also sort of not true. So most of the stars, like 75% of the stars in the sky, are way smaller than our sun. They're very dim. We call them red dwarfs. And actually, even perhaps more populous than those are brown dwarfs, which are so dim that you can't even really see them, except maybe with an infrared telescope. And actually, those brown dwarfs aren't much bigger than Jupiter. So the line between planet and star is actually pretty narrow, and it's really only separated by the ability to do fusion. Because remember, those brown dwarfs and those Jupiters are made out of the same stuff as stars. They're in the same proportion, more or less. Once you get cooled down to something like Jupiter, it tends to develop more complex molecules, but like 30,000 foot view, generally speaking, those brown dwarfs, Jupiters, they're basically the same composition. They have the same atoms in the same proportion as a star. There's just not enough of them for it to do fusion and shine really bright. So that's pretty weird and interesting by itself. How about Elliot? Are you in this class still? Don't know. All right. Anybody else? Thoughts? Talk to me. Yeah, Levin.
The thing about like there being another star in the solar system, you can't see it. Like, how would that be possible?
Yeah, that's a really, not in the solar system, but perhaps dancing around the solar system. I mean, all those hypotheses result from the bizarrety of us not having a partner and everybody else having a partner. So the proportion of stars that have binary partners goes up every year. The more faint stars we can see, more of these white dwarfs and so forth, the more likely it is that we will recategorize the solar system as having more than one star. Our star doesn't appear to have one, and every once in a while there's conjectures about whether we maybe do have one, like if our actual motion through the galaxy seems to reflect that we are orbiting something that we can't see. So how in the world would that happen is a reasonable question. Like if we had a partner star, would we be able to see it? Well, so there's probably probably the standard astronomical explanation would be no. We should see it, and if we don't, we probably don't have one. Okay, fair enough. So that may very well be the case. Maybe our solar system is very, very rare and unique, and we lost our partner star a long time ago. If it turns out that the motions do indicate that we have a partner star and they're just very slow, what could be the reason for that? Well, one possibility would be that it's a really dim red dwarf of some sort that we wouldn't see optically, right? It's only emitting infrared radiation, and we just haven't noticed the thing because maybe it's, 3-5 light years away, and we just haven't pointed our telescopes in the right direction. I think one of the things that maybe doesn't dawn on people, when they think about, oh, there's all these professional astronomers pointing their telescopes at the sky all day long, everywhere, all the time. Generally speaking, most of these really powerful telescopes are looking at a tiny little sliver of the sky, right? So they generally need to park their telescopes, even their space telescopes, in one place so it's shielded from the sunlight, so it's shielded from the earth light and all of that, the moon reflections. And they end up looking at a really narrow piece of the sky. And even when that's not the case, even when they're trying to survey different parts of the galaxy, they're still only able to look in one narrow little place at a time. So it's very hard to find something that you're not looking for. In fact, there's these heroic stories, particularly from last semester, of discovering new planets in the solar system, right? People didn't used to know about Neptune, for instance. They actually calculated from the strange orbits of the other planets that there should be another one there. So they noticed that the orbits were a little off, and the only way to explain that would be if there was another body out there beyond Uranus. And then they went looking for it exactly where they thought they'd find it, and sure enough, they found it. It just turns out that it's a huge planet, and it's really dim. You can't see it, actually. Even with a telescope, like with a consumer telescope, you're not going to see Neptune. It's very, very dim and very far away. So it's hard to find stuff you're not looking for. Another possibility would be that the star is very, like a lattice-based explanation for why we wouldn't see a partner star is a lot easier to come by as well, because you could run into a situation where a star is cooled down to the point that it's still pretty massive, but it's cold, and so its lattice has stopped emitting bright radiation. So the lattice-based interpretation of the HR diagram would be, in some sense, that stars cool down the main sequence. The standard explanation for the main sequence is a star starts on one point of that line, that cluster line thing, and it lives there its whole life. And eventually it burns out and has this whole heroic death to it, which we'll talk about in great detail. The sort of more mundane explanation, if you're willing to give us much more than 14 billion years for the universe to have been around, well, then you run into a situation where stars can just cool down the main sequence. And at some point, the stars are essentially completely invisible because they're so dark. They're not giving off light anymore. And so that's a very different approach to interpreting the lives and deaths of stars. You really get two different stories. That's why when I started this course and spent 3 weeks on the gaseous versus liquid sun, it matters in terms of so much of how we interpret the stars in the sky and their lives and deaths. You end up with two very different stories depending on whether you have liquid stars or gaseous stars. This is a gaseous star story from your textbook. This story of stars going through this, being born on one part of the main sequence, living, dying, and moving off of it. This is a very particular story that you can tell with a gaseous star that isn't quite as amenable to a liquid star story. So, yeah, the mystery's still out there. Do we have a partner or not? I think the jury's still out on that one. Kind of interesting. What are the thoughts? Anybody? Michael, yeah.
I guess I'm just curious where you draw the line with the stars cooling off and forming lattice and kind of molecularly like walking in place. Isn't it like the fusion and the ability to move around and fuse atoms like part of the definition of stars, doesn't it just become at that point?
Yes, that's exactly right. I mean, the Soviets had that idea actually back in the 70s. I think I brought this up at some point, but it's worth reiterating. So the Soviets, particularly this one biochemist, not even biochemist, but just a chemist named Oparin, wrote a book called Origin of Life. I'm not sure that's the proper translation of the Russian, but something like that. And he imagines actually that stars actually just cool off down the main sequence, and eventually they do form planets. And so the model coming out of that Soviet time was that planets were actually dead stars. Now, that would take trillions of years for that to happen. But I think, as far as I can tell, the only thing preventing us from considering that theory is that the age of the universe is only supposed to be 13.8 billion years old.
Yeah, I guess my question was just like, is that like the hard line definition? Like once it stops for one.
Yes. Yep, so bodies that can't fuse neutral hydrogen are not stars. Brown dwarfs do fusion, but they only fuse heavy hydrogen. So they don't glow quite as bright. They hardly glow at all, actually. But they're made out of the same stuff. They're roughly the same size as some of these dwarf stars, the red dwarfs, which are the most populous stars in the night sky. You just can't see them because they're so dim. So, yeah, two very different stories you can tell about this, depending on the material basis of the stars themselves, which is why that's such an important and interesting point. Yes?
So where's the sun located on that diagram?
That is a great question. So I want to say our star is a G-class star over here. So about down towards it's kind of middle of the road situation. Presumably, the standard model will have it drift off towards the red giants eventually, at which point it'll lose some layers and turn into a white dwarf. I think that's the standard model for our star. Of course, the liquid star model would have it just kind of cooling off down the main sequence for the most part. I think that this story of stars drifting off the main sequence is amenable to either a liquid or a gas model, actually. I just think that in the liquid model, it's kind of a rare situation. It's not, it's not the common way that a star would live out its life. It's sort of, well, we'll talk about it when we get there, because we're going to talk about pulsating stars and what it looks like for stars to drift off the main sequence. I think that works in either case. I mean, one thing that's quite interesting about this model, just from the standard story, from the textbook story, is that it's kind of weird that if the stars are supposed to live and die, all of them are supposed to eventually drift off this main sequence and become white dwarfs. It's kind of weird because we don't see that many of the white dwarfs. There's way more stars in the main sequence than there are in the white dwarf or even in the supergiant phase. Yeah.
Do you think maybe it happens just since they go so dim, they get so cold and just don't?
I think so, but I don't think that that's part of the standard model right now. And I think that it's all because of the gaseous story we've been telling for the last 100 years, basically. I mean, it's also constrained, it's hard for you guys to understand, but I really want you to understand why it matters. The story that we tell of the universe only being 13.8 billion years is geologically equivalent to it happened the universe started yesterday. It is really, really recently, geologically. In astronomical timescales, that is really, really recently. And, the question is how, actually, I think that this model for the 13.8 billion year old universe is actually gonna change really soon, maybe this year or very soon. There's already people proposing pushing that date back based on the new James Webb data. The question is, how much does it get pushed back? And does it get pushed back every time that we build a telescope that can see further into the past, can see further distances and therefore further into the past? Do you guys know what I mean when I say a big telescope can see further into the past? Does that make sense? Can somebody just explain that so that, yeah, I saw some people nodding their heads over there. Arthur, right?
Isn't it because of the time that it takes away from you? So obviously we're seeing things that have happened and that a lot of things may already be gone or old.
Exactly, yeah. So it's really, time and distance are the same concept, honestly, in physics, especially in astronomy. So, light travels at a constant speed. Therefore, if you know how long, right, if you know how far away something is, then you know how long it took to get there, and presumably you're looking way back into the beginning, or way back into the distance anyways. The problem is, right now with cosmology, that the further we look back in time, instead of seeing this primordial universe, we see something that looks more or less like our universe today. Galaxies are fully formed, they're mature, they don't look like something special necessarily. There's some caveats to that statement, and I'll break down the details of that later for you. But the point is, this date that we've come up with. So actually, my wife did this really interesting deep dive the other day with ChatGPT. And the age of the universe in the past 100 years has inflated drastically. I think that since the 1920s, it's gone from something like, 1 billion years to 2 billion to 3 billion to 6 billion. And with the latest telescopes, now we're at 13.8 billion. It just seems like every time we build a better telescope, we see further and we have to lengthen the age of the universe and kind of mess with the numbers as to how the redshift data, which we'll get to, fits into that story. My point is that the universe keeps getting older and older. And at some point, it gets old enough to actually tell a very different story about the HR diagram, which involves the cooling of these bodies in the absence of some dramatic explosive finale, which is the standard story for how stars die. So, two very different stories constrained by the cosmology, just constrained by the age of this universe, you know. Any other thoughts? Yeah, Lem. We're getting into it right now. But no, this whole course, honestly, I think by understanding all these details of why people think stars live and die the way they do, and how we interpret light, and how we interpret distance, which we're going to get into momentarily, is what is used to construct the story of the Big Bang. And we're going to see why the Big Bang became a popular idea. And we're going to see what it's up against today. Because, you know, in some sense, the Big Bang is the oldest story ever told on Earth. Actually, you find some version of the Big Bang in every culture going back thousands of years and even into prehistory. So it's an old story. It's more or less found in the Bible. It was found in the Sumerian folklore. It's found in indigenous traditions. This idea that the universe hatched out of an egg of some sort, a cosmic egg. It's very old. The question is, how did it become science? And so we'll work towards that. There's a couple of pillars that it really rests on, in addition to everything we've been talking about, but we have to understand how scientists construct the distance, right? How they construct how far away things are, how bright they are. The story that they're telling of the lives and deaths of stars goes into that story of the Big Bang, which is what this course is ultimately going to work up towards. But that story of the Big Bang is what constrains the dates that we have available to tell stories about things like the HR diagram, to tell stories about the origin of our own planet, to tell stories about the moon, right? To tell stories about everything. At the moment, all of those stories have to be told in under 13.8 billion years, which is a really short amount of time. I know it seems like a long time because you guys are like 20 years old, but 13.8 billion years is really, really fast, especially if you consider that the model of the Earth, you know, most geologists consider the Earth to be, you know, 4.5 billion years old. So you're only talking about 3 times the length of the Earth for the whole universe. And there's ontological, epistemological problems with that too, you know, like how do you know, is a story where something comes from nothing actually science? Is it? I mean, you know, is that a reasonable proposal? Like on its face? Like, can you actually spawn something from nothing and still really call it science with a straight face? You know, there's issues philosophically to delve into, but I hope that by the last week of this course, we can really take some of this apart, having absorbed the knowledge that goes into the construction of that Big Bang story. So, I don't know. I mean, my sense is, well, let's hold off until we actually get there. Any last questions or concerns? Yeah. Yes.
So types of stars that do not exist on the HR diagram.
Yeah, I think it goes into Michael's question, which is, what's the difference between a planet and a star? Because you could actually fit planets onto the HR diagram too. They will just be way off over here, trailing down in luminosity down into the dark region. But no, I mean, as far as luminous fusing stars that are doing fusion, they all seem to fit nicely onto this diagram as far as we can tell. Anything else? Yes?
I was wondering how we calculate the mass of stars from their orbits.
This was the binary spectroscopic method that we talked about. Can I put that in a sentence for you really quickly? You know, in some sense, it has to do with the basic principle that the faster something is going around a star, generally speaking, is in some way correlated to how big it is. and how close it is also. But I would have to refer you back to that lecture that we did previously, because that requires a huge build-up. Does anybody have a good way of simplifying that for her? Calculating the mass from the orbits of bodies. I know we talked about this briefly. Can anybody put that in there?
Each other, it's heavy, the heavier it is, the faster it's going. That's the, as soon as she asked the question.
Yeah, I mean, so yeah, it's tugging on things, right? So the orbits, generally speaking, if something is near something that's really heavy, it's going to be kind of like pulled close to it. The point between the two of them is going to be that they orbit. They're going to co-orbit a point. So like, if you have something that's really big and you have something that's kind of small over here, they're probably going to orbit a point closer to this big one. There's means of assessing, how far away something is, and by knowing how far away it is, which we're going to talk about today, and knowing how bright it appears, then you can use this like mass luminosity relationship, right? This is the thing that somebody brought up at the beginning of class. Bigger things tend to be brighter because they're doing more fusion. So if that's your assumption, then you can back calculate through the mass luminosity relationship, okay, it's this much brightness, therefore it's this much mass. It's not a perfect situation. It has a weird alpha parameter that I talked about in that's kind of choose your own adventure parameter. But generally speaking, the mass should be related to the true luminosity. The true luminosity can be calculated once you know the distance to the star and you know how bright it appears to be, right? So complex answer, but that's why we went through it in so much detail before. Yes?
Something I was thinking about was like, what will happen to the Earth if the sun did turn into a white?
Well, it depends which path of the choose your own adventure you go down, right? If you go on a liquid star model versus a gaseous star, you end up with two very different stories. The only way to a white dwarf in the gaseous model is a very terrifying explosion of the star, essentially. So that's not going to be good for Earth if that happens. Now, none of this, in either model, none of this is predicted to happen for billions of years, so you can sleep sound at night. In the liquid model, star just kind of cools off. Perhaps it also sheds layers, but its change, its dwarfiness is more a reflection of the fact that its lattice structure has changed in such a way that it's not as optically emissive. So it doesn't give off the same amount of light. Although, yeah, I think that's the best way to put it. So there's two different stories. We'll talk about both of them though. We're going to get more back into that. I need to make sure, you guys are wonderful. I love that you have so many questions. I do want to make sure we have time today to talk about the distance ladder a little bit, because this is another piece of the puzzle that's going to go into calculating, really what this means when we look at things that are 13 billion years away. How do we interpret it? How do we even know that they're 13 billion light years away? That's a really good question. But we have to check out distance to even make sense of that. So anybody's like burning a hole in their head, they need to get a question out really quick. All right, stop me as we go along if something comes up to you. So the goal of this is to construct some sort of system for measuring distance for really far away stuff, and that turns out to be pretty difficult, because the easiest way to measure distance is something that we see all the time, which is through this concept of parallax. Does anybody know off the top of their head what parallax is all about?
Isn't it kind of like where the, I guess where like a planet's supposed to be positioned next to the sun? Like, I guess when you're looking far away at a star, like compared to where like the planet is on its orbit, like the star will look like it's actually moving, but it's just not. It's just like parallax. Okay.
Yeah, I think an easy way to do this, we can like all do this. Actually, you can just use your finger. But if you put your finger like really close to your face and you close one eye and then close the other eye, the position of the finger moves. You guys notice that? Okay, so what's happening is you're basically setting up a triangle with your eyes between your eyes and your finger, right? And you're kind of averaging the location of that finger between the two eyes. This gives you a sense of how far away it is, actually. Now, the problem is, and I'm going to go through how this is calculated for stars in a second, but the problem is, now move your finger far away from your face and do the same thing. you notice that the finger doesn't move as much when it's farther away from your face. It moves a lot when it's really close up. Move it far away, it hardly moves at all, okay? So parallax is really, really good for stuff that's in our neighborhood that we can actually get a good readout on the difference, okay? But it's really, really crummy for stuff that's far away. And that's unfortunate because it's the most direct measure of distance that we can imagine. This, by the way, is the same concept that you see people doing when they make surveying estimates of how far something is away, right? So if you imagine like you're trying to build a highway or whatever, and you say, all right, this road needs to go this far before it curves and takes a bend, like how do they know how far a mile is away, right? I mean, they could go with a tape measure. Sometimes they actually do that with these wheeling tape measures, but a lot of it is just done optically through a very similar method to what we just did with our fingers. They do it through a parallax measurement. So let's check that out. The next thing for stuff that's further away than we can do with parallax comes down to looking at variable stars. So I want to talk about that a little bit today. And then the final and kind of most egregious method, well, there's another one we'll get to once we talk about supernovas and so forth. But another one is just looking at the HR diagram that we've constructed and kind of assuming how big something is based on where it fits on the HR diagram and back calculating the distance from the luminosity. So those are the three methods I want to look at today. Let's skip that. Okay, so before we get there, there's this word that we use all the time, space, right? What the heck is space? Anybody? This is actually, it seems like a really trivial question, but it's actually really important. Yeah.
A vacuum between planets and stars.
That is absolutely one way in which the word is used. What else? What else is space? What if I'm like, give me some space? What do I mean? Do I mean like, give me a vacuum, or what do I mean?
You go over there.
Yeah. Yeah, I mean distance, really, right? So this is where things get a little bit confusing. You know, it's nice when words mean different things in stuff like poetry or song lyrics or something, right? That's really fun. In science, it's a nightmare when words can mean two different things because you don't know whether the person explaining something to you means the one definition or the other. In physics, generally speaking, when we say space, what we really mean is a coordinate system of location, of specifying distances between different bodies, right? So generally speaking, going back to ancient times, the way that the coordinate system has been set up is in terms of length, width, and height. That is pretty much what space means to most physicists. It's a coordinate system of locating where we're talking about. And this has been extremely profitable across, thousands of years. But one thing that you have to be really careful with space is that it can also refer to, the regions outside of, Earth, right? People say going out into space or the space program, stuff like that. Well, they really just mean a region at that point, which in some sense is a contained within that coordinate system of location. But we have to be really careful because, it's very easy to turn space, which is an idea, it's a coordinate system of location, into some sort of physical body or some sort of actor object that we can do stuff with. Space is not a material. It's a concept. It's an idea. So you have to be really careful about that. So in terms of understanding how we can use distances and coordinate systems in order to locate how far away something might be, it's really funny because the way that we do it is using a piece of math that is super simple, and you guys probably learned about it back in middle school. And in some sense, it's one of the greatest achievements of mathematics ever, which is this thing. You guys ever seen this before? This is a Pythagorean theorem, right? Attributed apocryphally to this guy, Pythagoras, probably wasn't his idea. Lots of cultures have come up with this independently. But it's a really simple idea. It's like the area of this little square, if you make a right triangle out of some squares, the area of the a squared plus the b squared is going to equal the area of the c squared. This is just a matter of geometric fact. It just turns out to be the case. The wonderful thing about that is that if I can set up this kind of triangle system when I'm looking out into the distance, I can actually back calculate my distance to that object as a result of it. So, one of the famous examples in which this was used was the early Greeks. So I think this was like around 300 BC, like a couple of thousand, almost 3,000 years ago. Some ancient Greeks actually measured the circumference of the Earth using the Pythagorean theorem. So this is famously an example where there was basically a well that cast the sun would shine in at noon, and then some distance away, at the same time. By the way, they did have clocks back then, which is kind of hard to comprehend, but they had water clocks and what are those things called? Hourglasses, stuff like that. At the same time, some miles away, the sun would not cast, let's say, it would actually cast a shadow from a pillar at some neighboring town. And so what that resulted in is you could actually measure the angle of the shadow. You could do the opposite interior angles of that shadow. That's another theorem you guys probably learned about. Opposite interior angles of parallel rays are going to be equal, and you can back calculate the angle that triangle would form to the center of the Earth. If you have the angle, then you know what slice of the whole pie of the Earth that you're looking at. You know the distance between those two towns, and so you can just extrapolate to the size of the whole Earth. And they were actually pretty close to dead on when they did this calculation back 3,000 years ago. They actually came very close to nailing the actual circumference of the Earth when they did it. So it's a really, really profitable story for mathematics of how such a simple idea can be extrapolated to calculating enormous distances in this case. Turns out that actually the standard of measurement that we use today, the meter, you guys ever wonder where the heck the meter came from? Actually, it was some of Napoleon's engineers back in the 1700s divided essentially the circumference of the Earth, which was known from these calculations, into a very small amount. Let's see what did they actually write. They wrote that the meter would be the standard of length, and it was 1/10,000,000th of the length of the arc between the equator and the North Pole. So that's how they came up with the meter. They also standardized, a lot of other units in that time. So they decided that the kilogram was going to be the mass of a liter of water at the same time, and it's more or less defined that way to this day. There's new ways that we define the meter, though, today, which are based on the wavelength of light. These are called atomic clocks. We'll get back to atomic clocks later, because I have a bone to pick with them, but it's going to chew up our time to talk about distance if I go too deep into them right now. So let's get back to this distance measurement using the Pythagorean theorem. So this is basically how these surveyors do it as well, right? So what you do is you essentially set up this triangle. Now, what you do is you need to know a baseline that you can actually measure the base of. And this will relate to what David was talking about in a second with the solar system. And if you have this baseline, which you can measure just with a meter stick, or maybe you pace it out or whatever you want to do, and as a result of it, you actually have set up two identical right triangles as a result of it that you can use the Pythagorean theorem on. Now you do that essentially by back calculating the angle that results. So you're going to look at the angle that you need to align this thing with respect to the tree. That's going to give you this interior angle ultimately. And from that, you can use the trigonometric relationships and calculate the hypotenuse length just using the simple Pythagorean theorem. So you guys remember all the way back in middle school when you're doing the sine, cosine, tangent, all this stuff, right? This is essentially all working off of basic Pythagorean relationships. So the problem is that the further something is away, you need a bigger baseline, right? So these guys are looking at a tree in this diagram. That's pretty easy to see that parallax, right? You close one eye, or, your face is the same thing. You have a baseline, which is the distance between your eyes. So the reason that you see the location to be different is because you have two different locations that you're observing that from. So when we talk about actually doing this with stars, what do we use for the baseline? We use the biggest baseline that we can think of, which is the location of our planet in one season versus the opposite seasons, so spring and fall, or winter and summer, for instance. Because the Earth takes a year to go around a full orbit, that means half a year. It covers the maximum baseline distance, right? So I think this is what you were talking about, David. You were trying to. You were close, man. So the basic idea is that we can observe the location. We're trying to measure this red star in this case. And we can observe it from two different locations. We're going to end up with two different places for it, but the average of those is going to give us the location from it. And there's a really simple formula that we can use to take that angle and translate it back into distances. But the funny thing is that most astronomers actually don't even report the distances to objects in terms of meters. They don't even usually report them in terms of light years, although popular science really likes the light year for some reason. They report it in terms of things called parsecs. So you might be like, what the heck is a parsec? So this gets a little tricky. What they're actually doing, and this is the definition of a parsec essentially. What you're doing is you're writing a relationship where you look at the angle of separation that you get from that parallax measurement. In other words, the angle at which those two lines would intersect each other. And you're using that as a measure of distance. In other words, how much parallax is actually observable between 2 points with a standardization. And in the case of parsecs, which is the units that we use, the standardization is the Earth's baseline of orbit. So that astronomical unit is the baseline of one of those right triangles that we use in this parallax calculation. So what is a parsec? Let's see. A parsec is about, so the unit that it's going to give you of distance for 1 parsec is going to be equal to something like 3 times 10 to the 13th kilometers, which is something like 3.26 light years. So it's really, really far away. And when we start talking about the distances, we are going to be reaching into the hundreds and thousands of light years. And so parsecs just makes an easier way of talking about it. A little bit confusing, but what you guys need to remember is that this unit of measurement for distance is based on the way that we've calculated parallax to our nearby stars. And then we're transforming it into the more distant stars. So if you come across the word parsec, it all comes back to how much angle of separation exists in those parallax measurements and how that translates into light years. Yes?
So I talked about like the parallax in the video from last week for the assignment. And one of the questions I had were like, are there specific months out of the year that are best used to measure, and do different months provide different results? So like we're saying like the winter and like.
Yeah, you just want to have the biggest baseline possible, right? So it's like, it goes back to the finger experiment, right? The reason that your finger moves so much, in other words, that there's so much parallax when it's close to your face, is because the relative distance between your eyeballs and your finger and the baseline, the separation of your eyeballs, is greatest. So you want to maximize that baseline, right? And we obviously can't pull our eyeballs apart, so you have to move the finger closer. But if we were able to put the finger out here and move our eyeballs apart, we would still have a good deal of parallax that we could assess. So when it comes to using telescopes to do parallax experiments, the biggest distance you can get is 6 months apart. Makes sense, right? Because it does a whole circle every year. Every 6 months it does half a circle. That means you are as far away from that original point as you're ever going to be. So, what do I want to say about that? You know, it's really interesting because originally, people, when telescopes first came online, they couldn't actually see the parallax differences. And so they're actually really, really small for some of these stars. So when people were debating whether the Earth was at the center of the universe or not, one of the arguments for the Earth being at the center of the universe was that they couldn't actually measure motion of the stars. In other words, the parallax that they got for the stars was negligible. So even though they were looking at 6 months apart with these crude telescopes, they couldn't really even see much of a parallax angle. So if we go back, this is worth pointing out. I'm going to make sure I get these numbers right. But so a star with a parallax of 1/10 of an arc second. So what's an arc second? So remember, we divide the sky up into 360 degrees all around us. Really just 180 because we can't see underneath the Earth, right? Each one of those degrees can be divided again into 60 minutes. Each one of those 60 minutes within that degree can be divided into 60 seconds. So that means that in each degree is 1/3,600 arc seconds. So keeping that in mind, 1/10 of an arc second is like 10 parsecs away from us. So these tiny little distances is already like almost immeasurable levels of parallax is what we're able to observe with not the naked eye, but with crude telescopes. So it wasn't until they got really good telescopes that they were even able to see any parallax at all. So that's really interesting. It's not easy to see parallax even with stuff. So why weren't they able to see it? Because those stars are really, really far away. It's the equivalent of like taking your finger and like ripping it off your arm and moving it out into the parking lot. Like you're not going to see any parallax because it's too far away. Your baseline's too small. So parallax is extremely useful on Earth when we can control the distances and control the baseline that we're setting up, but it's really hard to use practically in astronomy. Although it does sort of it is the most direct measurement that we can do. Everything that we move on to from here is going to involve a good deal of theory about believing what it is we're looking at in terms of measuring these distances. And that gets kind of squishy and complicated too. All right. So they have like the latest telescopes. This is a mission called Parcos, which was launched in like late 80s, I think 89. They've actually measured the parallax. So what they do is, this is an interesting concept for you guys. There's these nice little points in an orbit for a planet. So what you see here is the sun. You see the Earth over here with the little moon going around it. When two bodies are orbiting each other, like the Earth and the sun, there's little gravitational null points where the pull from one is directly balanced by the pull from another. And if you were to stick some material there, like some asteroids or something, they would essentially just stay put. Oops, I lost my screen. They would essentially just stay put right in one of these L points. We call them Lagrange points. So there's a bunch of different ones. There's one closest to the sun on the other side of the moon called L1. There's a stable point on the other side, in the dark side. And there's several of these. So when we look at like Jupiter in our solar system, we'll find huge populations of meteors that just kind of hang out in Jupiter's Lagrange points, particularly in the L5 and L4 regions. They just kind of pile up there. We use this for satellites today. So we'll park our satellites, generally speaking, over at L2, because they'll just stay there. As we orbit around the sun, they'll just stay put in this nice dark patch, shielded from the sun's light over at L2. That's a really good place. So we put a satellite there, and we actually had it do these very tiny parallax calculations. And it was this is a map of all the different stars that were measured in the HR space, actually, luminosity versus temperature. So we have collected measurements for, I think 20,000 stars almost. This plot includes 16,000. I'm sure it's improved since this was made. So we have parallax measurements, but this was a really sophisticated satellite that was able to see tiny little changes in the angular location of those stars at both seasons, right, at each 6-month interval. They just couldn't do it back in the early days. They couldn't see they couldn't resolve with their instruments. They couldn't resolve those tiny little angular differences. To them, in spring and in fall, the stars seemed like it was basically in the same place. So that was really confusing. It seemed to argue that the Earth wasn't moving, is what it came down to. Because if the Earth was moving, those stars should have parallax, and they couldn't observe it back in the 1800s. So yeah, this is, it's tricky. It's not the most reliable method for things that are really, really far away. So the next method that we use for things that are far, far away is something called standard candles. So I don't know if you guys have come across this in your textbook yet, but this is kind of where we have to get into the theoretical space a little bit. The basic idea is that if we know, in this case, the population that we're going to be talking about are called Cepheid variable stars. So we know we can do some parallax measurement to find the distance to, let's say, this Cepheid constellation of stars. It turns out to be in the interior of the Milky Way when we point to it. So we can actually find some estimate of distance based not just on parallax, but also based on mass luminosity ideas, translating absolute brightness into the luminosity and figuring out the distance backwards that way. We think we have an idea of how far away these Cepheids are, right? This Cepheid cluster. It's a constellation, essentially, an asterism. What's really interesting is that there's a population of stars out there that does this really predictable change in luminosity. So it gets brighter over the course of days, and then it gets dimmer. It gets brighter and gets dimmer. And it turns out that this is a fairly reproducible common feature. We see stars throughout the galaxy. We actually see stars in other galaxies, or at least in the satellite galaxies around us, the mini galaxies around the Milky Way, that do the same exact pattern of brightening and dimming. And so the hope was that if we can figure out the distance, primarily probably through mass luminosity, to that Cepheid cluster, then we know every time that we see something doing this pattern of brightening and dimming, that we know how bright it truly is, because we know Cepheids are always this luminous. And so even if it seems dim, but it's doing this brightening and dimming, then we know that it's just further away. And so we can calculate the distance based on that. It's kind of like, going back to this bicycle versus truck on a country road at night thing, Is it a big object that's far away, or is it a small object that's very close to you? The idea is if you've standardized the candle, right, the Cepheid being the candle here, I know exactly how luminous this candle is. I can take it to any distance, and I know that as it dims, it's only going to reflect how far away it is. It's not going to reflect anything special that's changed. I haven't got a new kind of candle or something like that. So that was kind of the hopeful system in this case. The problem was that actually there turns out to be multiple populations of variable stars. And actually they used this system for, I want to say for a number of decades before they realized that there was actually two very different Cepheid populations. And they actually had to double the distance of everything in the galaxy at one point. There's a man named Walter Beatty who did all of this work to show that there were actually two distinct kinds of Cepheids that did very similar patterns, but in fact were not the same type of star. And so the whole galaxy actually expanded by a 2x pretty much overnight back. I believe this was back in the 40s. So you can start to see how these assumptions that you make about what the star actually is are going to start to feed into how far away we think they are. And so these distance measurements that we start setting up, especially when we start looking at other galaxies, become very theoretically grounded as opposed to direct measurements like you would be able to do with parallax. It would be wonderful if we could do parallax for everything because it's geometric, it's very reliable, we use it for surveying here on Earth. The problem is you need a huge baseline to really pull off accurate parallax measurements. So we don't have that. The variable stars are kind of interesting because they also feed into the story that we were telling about the HR diagram. Why in the world would a star be pulsating like this? And we're going to get back to this. We're going to get back on track with the lives and deaths of stars soon. But just to sort of preview the idea, the gaseous explanation, of course, is that when something gets dimmer, its radius has to shrink, right? That's the only way that in a gaseous star you can get something to be appropriately hot but dim, right? The temperature doesn't change of these stars. The brightness changes of them. So they imagine, using the gaseous model of the stars, that these pulsating stars are legitimately getting larger and then shrinking, getting larger and shrinking. With a liquid model of the stars, you can get yourself in a very different explanation where you're just cycling the actual lattice arrangement of the atoms on the surface and getting different optical properties. So two very different possibilities for what these pulsating stars actually represent. But there are plenty of them that appear to be pulsating. There's one actually you can see with your naked eye called Betelgeuse. You guys ever see Betelgeuse in the sky before? It's not a Cepheid, but it is a pulsating star. So if you go out, you guys ever see Orion in the sky? It's one of the easiest things to see. A little bit, yeah. So there's like a cluster of 3 big bright stars in the night sky. You can see it almost every night. If you look, so that's, it's supposed to, in the constellation, that's kind of the belt of this hunter. If you look let's think about this. If you look, I believe it's in his upper left shoulder, there's kind of a big yellowy red star up there. And it actually changes in brightness from day to day. And if you start paying attention to it when you're walking around at night, you'll notice that it really does seem brighter some days than others. And that is presumably a pulsating star that is going through some stage in its life that we have yet to reconcile in our story here. So that's pulsating stars. There's also another form of pulsating stars called RR Lyrae stars. Again, very similar piece of the puzzle. These are thought to be stars that are moving off the main sequence and moving into the red giant phase of their lives. Don't worry, we will return to that very soon. These stories are very much complicated. It turns out that as people are starting to study the composition of these stars, they're noticing that how much metal content the stars has really affects their period as well. There's other factors that go into it. So it's not perfect. It's not a perfect standard candle, but it's kind of the best we can do because judging the distance to things turns out to be really, really hard when you can't do these direct parallax measurements. So, this brings us full circle back to the HR diagram, because the final way that people will judge the distance to stars, there's one more we'll get to when we talk about supernova, but the final way is by looking at them on the HR diagram and trying to back calculate from their luminosity how far away they are. This is actually called spectroscopic parallax, which is a hilarious name because it has absolutely nothing to do with parallax. There's no parallax measurements involved in it whatsoever. But the hope is that by assigning a star properly to the HR diagram, that you know its true luminosity as a result and you can back calculate it. So those are our 3 methods that we're left with. We have the fantastic trigonometric parallax, which is good here on Earth. We have some of these pulsating variable stars. And what you can see is that some of them are good to further distances than others, right? We can actually observe Cepheid stars that are really, really far away, so 60 billion light years away. That'll get us pretty far into the picture, but it won't get us into distant galaxies. So we're going to need something else for distant galaxies. We're going to need a different standard candle, and that turns out to be the supernova, which we'll talk about very soon. All right. Questions about this distance construction before we depart from the distance discussion for the moment? I know this is very, very technical, and I apologize for that, but I think that it is important for us to understand how in the world we believe that we know how far away something is, because it's not a straightforward drag your ruler out and measure it kind of situation. It's actually quite tricky and very much grounded in theoretical assumptions about what these stars are. Yeah.
Why did they add parallax to the HR diagram if it doesn't have
I have no idea. Maybe somebody can. I have no idea. Honestly, it boggles the mind. I have no idea. I'm sorry. I'll see if I can figure that out for you for next time. Anybody else? All right. Well, the next thing we're going to go into is going to be a block on the stuff in between stars and the building blocks of stars. I don't see any reason to start that today, but let's get into it on Thursday, and I'll try to review some of this so that we can be sure that it's stuck in our minds. But yeah, have a good week, guys, and I'll see you on Thursday.